Hello everyone, I am Vuln from and Financial Tianqiong Security Lab. I am a security expert interested in software security and sensor security. The topic I bring to you is explore deficiencies in the state-of-the-art automatic software vulnerability mining technologies. The content of the topic includes several situations that cannot be solved by the current vulnerability mining tools, and some experiments and ideas that imitate manual code review. First of all, I want to clarify our target. Our target is to find a way to make the vulnerability mining completely done by the machine, and its efficiency reaches or exceeds manual. In order to achieve this target, we hope to find the deficiencies in the existing vulnerability mining technologies and try to improve them. When we want to use tools to help us find vulnerabilities in software, we usually need to do some preparations to achieve the desired results. Possible preparations are finding the magic numbers or keywords in the code to construct the dictionary, removing codes that prevent effective testing, such as checksum function in libPNG, preparing a large number of seed files that can run into different code blocks, writing programs that use random numbers to generate valid data, calling the API selectively to ensure that the specified code can be tested. These preparations are often emphasized by the tool itself as necessary. Some seed files must be provided to AFL to work properly, and each preparation usually only deals with one type of code. You need to make different preparations for different code. If you start fuzzing from scratch, the fuzz process will soon get stuck. In fact, these preparations are to make up for the lack of tool capabilities. Before introducing the deficiencies of current technologies, we must first understand them. The current tool mainly uses two core algorithms. One is feedback-driven genetic algorithm, and the other is symbolic execution. Feedback-driven genetic algorithm is the core algorithm of AFL and libFuzzer. The algorithm obtains internal information of the program as feedback by instrumenting the target program. The algorithm attempts to generate new test cases that can improve the coverage rate by using these feedbacks. The ability of this algorithm depends on the content of the feedback and the ability of using these feedbacks. I do not discuss the implementation details of all technologies. We only focus on the part that has an essential impact on the ability of the algorithm. For feedback-driven genetic algorithms, the method of obtaining and using feedback determines the effect. LLVM CLAN and GCC compilers now come with TracePC, TraceCMP compilation options for obtaining feedback. Address sanitizer and thread sanitizer options for detecting unexpected behaviors. With the TracePC option, we can obtain code block, path, and depth information. Using this information, various coverage rates can be calculated. With TraceCMP option, we can obtain the left value and the right value of comparison in the conditional statement. By calculating the similarity between the left and the right values, we can select use cases with higher similarities, making new use case that can go to a new branch more likely. Execution is like a small virtual machine. Symbolic execution finds the conditions that constitute a bug by trying to traverse all feasible paths. Modern tools combine genetic algorithms and symbolic execution to find a bug. We call these tools hybrid fuzz or concolic execution. These tools first find a set of concrete paths by using libFuzzer or AFL, and then find new branches along these concrete paths, and try to use symbolic execution to construct data that can go into new branch. However, the problem of path explosion still exists, and it is not always possible to find new branches in the concrete path. In order to show the deficiencies concisely, I wrote a few lines of code as an example. I put a null pointer access as a bug inside a conditional statement until I finished the test. The official AFL could not complete the guessing of the 4-byte integer. In other words, a magic number can still prevent AFL from working. In this code example, if libFuzzer or AFL wants to cause a null pointer access, it must construct a memory containing two 4-byte integers and ensure that these two integers are within their specific ranges and equal to specific value after multiplication. In this example, neither libFuzzer nor AFL can construct an input that can cause a null pointer access. This is just one of the situations blocking libFuzzer and AFL, and I will explain why later. In this example, to cause a null pointer access, all bits of variable flag must be set to 1. If you want all the bits to be 1, you must meet all the conditions. Not only libFuzzer and AFL, but KLEE and QSYM will not construct the data that caused the bug, because they will not take the initiative to meet all the conditions. I believe that neither traditional symbolic execution nor improved hybrid fuzz will do that. The path explosion is not our excuse. Our target is to find bugs, not to solve the path explosion itself. As a programmer, you can find the conditions that cause the bug at a glance. Why not let the program do it? I have put all the code that can prevent the fuzz tools from working on GitHub. The compilation and the testing steps have been written in the bash script. You can download and reproduce my test, or use it to test your own tools. The yes in the table indicates that this source code can be used to test the corresponding tool. The reason why ibFuzzer and AFL cannot find vulnerabilities is that they cannot solve constraints that cannot be approximated. In order to make the constructed test case into a new branch, libFuzzer inserts stops before every conditional statement when the target program is compiling. When target program is running, libFuzzer obtains the left and the right values for comparison in the conditional statement. libFuzzer uses a variety of distance algorithms to calculate the similarity between the left and the right values, and selects the use case with a smaller distance to keep, and finally achieve the approach to the condition. Some improved AFL will split the magic number into bytes. Every time a byte is guessed, AFL will get a feedback. After all the bytes have been guessed, the magic number is constructed by the AFL. The code shown in the previous slide that can block libFuzzer and AFL contains a pair of values that cannot be approximated. The reason why symbolic execution can enter a new branch on the basis of libFuzzer or AFL is because they can solve the inapproximable constraints. Now I take the code of libFuzzer as a specific example to explain why it cannot find the null pointer access. With the decompilation tool, we can find that libFuzzer inserts a callback before each comparison operation. ibFuzzer uses callbacks to get the left value and the right value involved in the comparison operation. We also found that the callback does not contain information about the operator of comparison, because the operator of comparison has no effect on the utility of the approximation algorithm. Here is the implementation of the callbacks by ibFuzzer. We found that it not only instrumented before each comparison operation, but also instrumented some external functions for comparison. In addition to memory compare, the instrumented functions include string compare, string case compare, etc. It is very rare and difficult to be equal in the case of random generation. I think the author's idea of libFuzzer is to achieve equality first, and the state of greater than or less than after the equal state has a great probability of appearing. libFuzzer uses two distance algorithms, Hamming distance and absolute distance. The Hamming distance between two memories is the number of positions at which the corresponding bits are different. The smaller the Hamming distance or absolute value distance, the higher the similarity between two values in a certain type. I think that Hamming distance describes a nonlinear relationship, while absolute distance describes a linear relationship. Unfortunately, there are many functions that are too difficult to approximate, and the existing value and the target value often cannot be approximated at the two distance of Hamming and absolute. In other words, if there is a function in your research project that cannot be approximated by Hamming and absolute distance, the code that needs this function to meet certain conditions to run may be the code that libFuzzer cannot reach. Path explosion is an ancient problem for symbolic execution. Our target is to find a path to form a vulnerability, not to increase the coverage rate or solve the path explosion. The codes in the previous slide that block QSYM and KLEE is simplified as shown here. If the formation of a vulnerability needs to satisfy multiple conditions at the same time, or requires a program to take a specific path, then the general symbolic execution will not find these vulnerabilities. The general symbolic execution is faced with infinitely selectable conditions and infinitely selectable paths. It is difficult to determine which conditions are satisfied to form a vulnerability. General symbolic execution wastes a lot of resources on work that never find vulnerabilities. I believe I have found 3 rules. Since vulnerabilities are increasingly appearing in rare locations, this method of increasing the probability of finding vulnerabilities by increasing the rate of coverage has become less and less effective. Although exhaustion is the strength of the machine, it cannot handle the exponentially increasing number of paths. We need to choose a path that is worth following. Some constraints cannot be solved with general approximation algorithms. We still need a constraint solver to check whether the path can pass. I usually look for vulnerabilities like this. In this example, I found that a sufficient and necessary condition for null point access to occur is that the flag bits are all 1. In order to meet the conditions, I will look for how the flag variable is written and look for the conditions that trigger the right action. Then ensure these conditions can also be met. In other words, I try to find a code path that sufficient conditions for vulnerability can be met. In mathematics, a constraint is a condition of optimization problem that the solution must satisfy. So what I do is to find a path to satisfy constraints in reverse. I found that any vulnerability can be described by a set of sufficient and necessary constraints. The previous null point access vulnerability can be described as the constraint variable flags equal to hexFF, and the memory copy overflow vulnerability can be described as the constraint variable size being greater than the distance memory size, or the variable size being greater than the source memory size. The first thing in manual code review is to assume that these constraints are solvable. I think manual code review can be divided into 3 steps briefly. First, assume the constraints that make vulnerabilities exist can be satisfied. Second, choose a path that allows the constraint to propagate to the new variable in the opposite direction of the variable assignment. I call it variable constraint backpropagation. Third, in the process of backpropagation, we can check the satisfiability of the constraint to determine whether this path may satisfy the assumption. This diagram explains the way backpropagation is done by showing changes in constraint expressions. Suppose we found that the condition for forming the vulnerability is that V0 is equal to hexFF. Following the reverse path of a certain program, we found that V0 comes from V1 bitwise or H0. We replace the symbolic expression V0 in the constraint expression with the OR operation expression of V1 bitwise or H0. If following a specific path needs to satisfy a specific constraint, we will add this constraint to the constraint expression with logical AND expression. In an ideal state, when all the symbols in the constraint expression are input, we can solve the constraint to get an input that forms the vulnerability. The construction process of constraint expression in variable constraint backpropagation is different from that in traditional symbolic execution. It replaces the symbols in the original expressions with expressions containing new symbols, rather than continuing to split the input symbols like symbolic execution. The slide shows my implementation of replacing symbolic expressions with new expressions in constraint expressions. I use the map data structure to store all symbolic expressions corresponding to a same symbol to facilitate replacement operations. I duplicate the new expression for every symbolic expression one by one. I verified the feasibility of variable constraint backpropagation based on the LLVM bitcode. In LLVM bitcode example, the null pointer access is in code block 148. The condition for jumping to the code block 148 is that variable 147 is true. The variable 147 comes from whether the variable 146 is equal to -1. Now the judgment that the variable 146 is equal to -1 must be true. The variable 146 comes from a variable in one of the two code blocks. At this time, the constraint expression is forked. If the variable 144 in a code block 134 is selected, the variable 146 is replaced with the variable 144. This is a piece of backpropagation demo code for bitwise AND operation. The current variable is calculated by the bitwise AND of two variables. The code first constructs two variables into two symbolic expressions and add them to the bitwise AND expression. Then replace all symbolic expression corresponding to the current variable with the constructed bitwise AND expression. Then delete the current variable from the variables that need to be backpropagated, and insert the two variables in the bitwise AND operation. Add the new variables to the list that needs to be backpropagated. In order to solve the code blocking KLEE and QSYM, I wrote a series of backpropagation codes of instructions. These boring codes are not shown here now. Now I will show you my variable constraint backpropagation demo code that can solve the code that block QSYM, KLEE, AFL, and libFuzzer. Here is the code that block QSYM, KLEE, AFL, and libFuzzer. Only when all the conditions are met will the null pointer access be triggered. Here is the null pointer access. Here is LLVM bitcode, compiled from the previous C code. The null pointer access in LLVM bitcode is here. I divided the demo code into a constraint expression module and a backpropagation module. In the running process, we will see the construction of the constraint expression and the search process of the reverse path. This will run for a short period of time, because even the constraint solver is quite time-consuming to solve inapproximable constraints. In the end, the demo will print out a solution which shows what 4-byte integer value should be in which byte offset of the input data. This is constraint expression for null pointer access. The solution just now is obtained by solving this expression. I think if you want to use code to imitate manual code review, there are at least 4 things to do. First, we have to determine what is unaccepted behaviors in the code and construct the initial constraints that make the vulnerability exist. I consider to take a set of sufficient and necessary constraints as an assumption. We can use address sanitizer and the asserts to help us establish the assumptions. Second, we still need to use libFuzzer or AFL to help us quickly find multiple concrete paths when virtual execution is too slow and unnecessary. Third, due to the limitations of dynamic function pointers, external functions, and computing power, the distance of backpropagation is usually limited. Fourth, although the distance of backpropagation will be limited, we can still use some approximation algorithms or fuzz tools to try to solve a set of sufficient constraints. As a bug hunter, I have something to say. If you are only interested in vulnerabilities, I suggest that you just use the existing tools. You should only write tools if you are interested in the work itself. Otherwise, others have found a bunch of vulnerabilities by manual code review, but you are still tossing about tools. That will blow down your confidence. Thank you for listening to my speech. I hope my shared content is useful to you.
Thanks for your talk. We've got a couple of questions. I'm not sure if you can see the screen. But the first one is, how would this approach scale compared to a more popular grammar rule-based fuzzer?
If you want to write a good grammar or rule-based fuzzer, you still need to read the codes you researched. So you also need to understand what happened in the target you want to research. My target is to let the work completely done by the machines. So my research about the variable back propagation is about the use a way to do this work by the machine, not the human.
Okay, thank you. There's one more question by Ali Mutu Ahok. Interesting approach. Do you publish any white paper based on this hybrid fuzzing approach? Like to learn more about it?
No, I don't have time to write such a wide paper because I have other work in my company. Sorry.
Okay, no worries. I think that's all the questions we have. Thank you so much, Wish, for your talk and for taking the time to answer the questions.